So what is the difference then? Well, first of all, I think we've got to recap SN1 and SN2. So SN1, 1, 2, 3, bang, is how I remember it. So SN1 is a two-step reaction with tertiary haloalkane, and bang means it's fast. So comparing SN1 and SN2, you can see that SN1 has two steps, corresponding to those two peaks on the energy profile, and SN2 just has one step. All right. Now let's look at the speed, the bang. So reaction coordinate, you can also think of that as time. So you can see that the time for this reaction, SN1, is shorter than the time for this reaction, SN2. SN2 is the slower reaction. Let's go back and look in detail at SN1. So let's choose 2-methyl-2-fluoropropane as my tertiary haloalkane. Fluorine has a high electronegativity, grabs those electrons. So the activated complex is going to be this, leaving me with the reaction intermediate of that. Now that takes a lot of energy to do. It has a high activation energy. In fact, in this two-step process, that's the slow step. Moving on now, I'm going to add the OH minus. I've got no room to put the activated complex, but let's go all the way down and show the final product. So with the SN1, S is substitution. Yep, I'm swapping out the fluorine for the OH minus. N is nucleophilic. Nucleophiles love nuclei, they're positive. So the OH minus is the nucleophile. And 1 is the molecularity of the rate determining step. So the first step has only one molecule in it, and the second step has two reacting molecules in it. So SN1, so the slow step, the rate determining step, is going to be the one with just one reactant. So it's this one. So if that's the rate determining step, that's going to be the slow step. So it has to have the highest activation energy. So this first step here has a much higher activation energy. Oh, I missed that. Sometimes the IB are a bit fussy. I don't know how fussy they could be. So, and then the second step has a much lower activation energy. So that will be faster. Looking at SN2, well, SN2 is a one-step process. That makes sense. It's only got one bump there. And it's to do with primary haloalkanes. Just looking at the opposite of what I wrote before. And that's the slow step. So there's only one step. Now, the two here, again, is the molecularity of the rate determining step. The slow step has two molecules. There's only one step, so it has to be that one step. Now, since this whole reaction is slow relative to the fast reaction of SN1, it's going to have a bigger activation energy, and indeed it does. It's much bigger. Just for completion, let's draw out the reaction. So those electrons go there. Those go onto the carbon. My activated complex. And don't forget the cheeky minus on your activated complex. Going down to the product. Alrighty, so two molecules in the rate determining step, and there they are. It's those two there. So the only other question I think they could ask is, well, what happened if you replace the fluorine with another halogen, such as iodine? So if I had the iodine version, the bond between the carbon and the iodine is a lot weaker than the bond between the carbon and the fluorine. So if it's a weaker bond, I imagine the reaction is going to go faster, and I imagine the activation energy is going to be lower. So activation energy is lower, and it finishes sooner. Now the rest of the reaction, I think, is it's going to be the same because it's the exact same two chemicals. It will be this one here, this carbocation, and the OH minus reacting. So for this second part of the reaction, I think it's going to be the same. And over with the SN2, if I was to replace that fluorinated alkane with one with iodine on it, it will have a lower activation energy and it will finish quicker, but at the same level because it's going to be the same products. Okay, and we're done.